So last time we formalized the notion of a category a little bit. It's a pair consisting of a contract for what constitutes a morphism together with a way of composing the morphisms. So we saw that if we have a pair of integers where the first one is less than or equal to the second one, we can use the transitive law together with this contract to make a category, LEQ. Similarly, given a pair of integers where the first one is a factor of the second one, we can also use the transitive law to get a category. And this works for any partial order. We saw that we could use guarded functions. Instead of using a pair, we have a triple here. The input contract, the output contract, and a guarded function mapping between them. And then composition is just what you'd expect. The input contract of before, the output contract of after, and composition of the functions. And that gives us contract guard. Also showed how to make a contract for monoid homomorphisms, which has a very similar structure. Has an input contract, an output contract, and a function mapping between them. And then we compose, well, we do just the same thing when we're composing them. We get this category mon. So up here we see partial orders give categories, and here we see that monoids with monoid homomorphisms give a category, and here we'll see that individual monoids themselves give categories. So this has an element of a monoid being a morphism. So here I've got before and after and middle are all numbers. And the way I compose these numbers is using addition. This was going overboard because I was trying to use integers, but if I'm just using numbers, I can just multiply them. So here are two different ways to get a category from numbers. This should be num. I can either add the numbers or multiply the numbers as my composition operation. Now if I have a monoid, I can get a category from it by saying something like this: var from monoid is a function m, return category m.t. So the elements of the monoid are the things that pass the contract for morphisms, and function before, after, m.t before, after equals m.t of after, return function middle equals m.t middle, return after this m bracket times after and m bracket times there. Right, so there's the end of that semicolon. There. So now given any monoid, M, we can construct a category from it whose morphisms are the elements of the monoid and whose composition function is simply the times function here. So we see that not only do we get categories from structures like groups or monoids or fields or rings or sets or vector spaces and the structure preserving maps between them, but we can also see that some structures themselves are categories themselves.